Welcome to Hindalco Silvassa Zero Liquid Discharge Plant. The Zero Liquid Discharge Plant processing capacity is 450 kiloliters per day. The 450 KLD wastewater treatment plant. The plant is designed to achieve zero liquid discharge, ensuring no liquid wastewater leaves the facility. The plant treats mixed effluent from various sources, such as process wastewater, utilities wastewater, dewatering machine centrate, and other wastewater generated from the facility. Let's walk through each step of this comprehensive process. Screening. The process begins with the removal of coarse materials, such as plastics, rags, and large debris using manual screens. This crucial step prevents blockages and protects downstream equipment from damage, ensuring smooth operation in subsequent stages. Oil and grease chamber. After screening, the wastewater flows into the oil and grease chamber, where free-floating oil and grease are separated through gravity-based skimming. The lighter oil particles rise to the surface and are removed using a belt skimmer. This step reduces the risk of fouling in later treatment units, ensuring long-term efficiency. Equalization tank. The equalization tank plays a key role in stabilizing both the flow rate and pollutant load. It acts as a buffer, preventing sudden surges of high-concentration wastewater. Air diffusers installed in the tank provide continuous mixing, preventing solids from settling at the bottom and maintaining uniform characteristics throughout the wastewater. Primary chemical treatment. In this step, the stabilized wastewater undergoes chemical treatment to remove contaminants like suspended solids, chemical oxygen demand, and biochemical oxygen demand. The treatment involves a series of chemical additions to ensure effective pollutant removal. Lime is added to adjust the pH level, improving the coagulation process and minimizing scaling. Coagulant destabilizes the particles, allowing them to form larger flocks. Polymer enhances flock structure, making it easier for solids to settle in the clarifier. The flocculated particles settle in the clarifier, separating clean water at the top and sludge at the bottom. The clarified water is sent to the next stage, while the sludge is directed to the sludge handling system for further processing. Sludge handling and dewatering. Sludge from the clarifier is pumped into the sludge tank, where it is mixed and homogenized to ensure consistency. This prevents settling and facilitates efficient dewatering in the next step. In the screw press, the sludge undergoes a continuous dewatering process. A flocculant is added to improve separation efficiency, allowing water to be squeezed out as the sludge moves through the thickening and dewatering zones. The final output is a thickened sludge cake with reduced moisture content, ready for disposal. Tertiary treatment. The clarified water from the primary treatment undergoes advanced filtration to ensure high water quality for the reverse osmosis (RO) system. Pressure sand filter removes finer suspended solids that escaped earlier stages. Ultrafiltration (UF) uses hollow fiber membranes to remove microscopic particles, colloids, and microorganisms, ensuring a high level of water purity before RO treatment. The two-stage RO system ensures efficient recovery of high-quality water. Stage 1 recovers up to 85% of the water while removing most dissolved salts. Stage 2 recovers up to an additional 55% from the brine left over from Stage 1. With an overall hydraulic recovery of approximately 92%, only small volume of brine is sent for further treatment in the mechanical vapor compression-based evaporator system. MVR chemical pretreatment. Before entering the mechanical vapor recompression (MVR) unit, the high salinity reject from the last stage of RO system undergoes chemical pretreatment. This step removes suspended solids, hardness, and silica to prevent scaling and fouling in the MVR system. A dedicated filter press system handles the sludge generated during this chemical pretreatment, ensuring efficient solid-liquid separation. Mechanical vapor recompression (MVR). In the MVR system, pre-treated water is evaporated through mechanical vapor recompression, an advanced and energy-efficient process. A key component of this system is the MVR blower, which compresses the extracted vapor, increasing its pressure and temperature. This compressed vapor is reused as a heat source to evaporate more water, significantly reducing the system's energy consumption compared to conventional evaporation methods. The system continuously recycles the latent heat of the vapor to maximize water recovery while minimizing operating costs. The evaporated water is collected as high-purity condensate, while the concentrated brine is sent to the agitated thin film dryer (ATFD) for further processing and complete moisture removal. The concentrated brine from the MVR and anodizing plant evaporator is fed into the finishing evaporator followed by an ATFD. To reduce the heat load to the ATFD, the feed is further passed through a finishing stage thermal evaporator prior to admitting the same to the ATFD. The concentrated stream of slurry is thinly spread across the periphery of the ATFD. The moisture is quickly evaporated, leaving behind dry salts or powdery residue on the circumferential ATFD shell, which is scraped off completely by a zero-tolerance scrapping mechanism. This step ensures that no liquid waste is discharged from the plant, aligning with the ZLD objective. Steam boiler system. A compact coil type, non-IBR boiler supplies the necessary steam for the process. The boiler feed water is polished to maintain high quality, ensuring efficient operation and preventing scaling or corrosion in the boiler system. Condensate reuse. To further enhance water efficiency, condensate generated from the MVR and ATFD processes is collected and reused as utility makeup water. This reuse contributes significantly to achieving the plant's zero liquid discharge (ZLD) goal.